Hi guys, so in this video we'll be going over chapter 1.5 part 2 forces continued, and we'll be once again going point by point, and this chapter is a bit longer, so this will take a bit more time than the usual videos and whatnot, and we'll be again going alongside Z notes. This time we might have to use the notes a bit, but I'm not really sure, so yeah, we'll start and we'll see if we need the notes or not. So let us start on point 1. Describe friction as force that may impede and produce heating, impede motion and produce heating. So this is kind of a filler thing, impede motion. Basically, force will always go against motion, like this is a given, this is common knowledge. And friction will usually produce heat and whatnot, and convert your energy into heat. So this is just common knowledge. There is really not much in depth or anything to describe here. And point 2, understand the motion of objects acted on by a constant weight or driving force with and without drag. So objects under motion, and we can give simple examples over here. So imagine a car is moving, towards the right, and the engine is providing 20 newtons towards the right, and this force is moving the car towards the right. So this is called the driving force of the car. And without drag, this is the motion. The car is going towards the right with 20 newtons continuously. There is nothing going against the car, right? There is no friction force, there is no air resistance. So as the car is, having a net positive, resultant force towards the right, the car will keep accelerating. By using the formula F equals ma, we can see if there is a resultant force, the car will accelerate. So let's just say 20 equals the mass is, our mass would be, let us say 2 kg into a. So if we side change, like 10 equals, so acceleration would be 10 meters per second square. So if there is a resultant force, there is acceleration. Do keep that in mind going forward. And this time there is no drag or without drag. What if we have drag? So if we have drag, let's just say the drag is 20 newtons per second. So 20 newtons continuously towards the left. So this is the friction force or drag. So now the forces cancel each other out, and now the car will either move at constant speed, there is no acceleration, acceleration is zero, but the speed is still there. If the car was moving towards the right, it will keep moving towards the right, there will be no change. If the car was stationary, the car will stay stationary, the car will not move. So this is more or less it, with and without drag. Questions usually do not come any harder than this. You'll just have to know that what is the driving force, and the drag is gonna act against the car's motion and whatnot. So explain how an object reaches terminal velocity. So how does an object reach terminal velocity? When the weight, the force due to the weight, and the drag, they both are canceling each other out. So imagine someone jumped from a plane. So let's just say they are now falling downwards, and they're falling downwards with their weight. So your mass multiplied by gravity, that would be, let's just say 50 newtons will be your weight. And if you're falling down with this weight in air, air resistance will push against you. And this air resistance pushing against you will start at, let's just say, very low. When your speed is very low, right? The air particles, they will come up to you and collide with you. So if your speed is very low, the air particles that will come up and collide with you will have less energy. But when you're moving very, very fast, and if you're moving very, very fast, then you'll cover a lot of distance. So a lot of air particles will hit you per second and whatnot. And the air resistance will increase. So this is generally how air resistance works. Air particles come up to you and hit you, and they try to stop you. And as more and more air particles hit you, your speed decreases or stuff like that. So when air resistance slowly increases and increases as your speed is increasing, right? So air resistance is increasing. Air resistance becomes 50 newtons at some point. Then your weight 50 newtons and air resistance, they cancel each other out, so you are not accelerating anymore. The moment you stop accelerating in free fall, when you are falling freely through air, then this is called terminal velocity, because your velocity will not increase, it will not go up after this point as you have stopped accelerating. Your upwards and your downwards force, they have both cancelled each other out, and so you will maintain the speed you are going at. The forces do not go away. Keep in mind, the force due to your weight is still gonna push you downwards, and the force due to air resistance will still try to push you upwards, but they will just cancel each other out. They will be there but cancel each other out. If you take the air resistance out of the equation, then the weight will accelerate you downwards. Or if you throw out the weight, the air resistance will try to push you, move you upwards, accelerate you upwards. So this is terminal velocity, the moment you stop accelerating, in short. So define thinking distance, braking distance, and whatnot. What is thinking distance and braking distance? So imagine a car is going through a highway this way, and the car sees a tree. The car sees a tree and it has to brake. So first you will look at the car, then you will think, okay, I need to brake. Then you'll give your body will give the muscles in your brain will give the muscles in your body the order to, let's just say, press the brake pedal and whatnot. And then when the brake pedals are pressed, the tires will lock up and then slow you down by friction. So there's a lot of things being happening, right? There's a lot of things happening. Your body is doing something, your car is doing something, friction and whatnot. So these are divided into the thinking distance, braking distance. Thinking distance is the amount of time a human needs to see the tree and realize, okay, I need to brake. This is the thinking distance. And thinking distance is usually pretty average from human to human. It does not really deviate much. It's like how much? 200 milliseconds to 400 milliseconds, something like that on average. And braking distance. Braking distance is the amount of time your car takes to stop. So if you press the brakes at here, right? You press the brakes at this point, your tires will lock up and the friction on the road will try to stop you. And after a point of time, enough friction will stop your car. So this is the, let's just say, distance and amount of friction needed to stop your car. So thinking distance, braking distance, and stopping distance is the total time. Total time will be this, let's just say, because you have to think for a bit of time. Or I should draw here. So this is the time you took, right? You saw the tree over here and your body realized, okay, I need to press the brake. So and you press the brake at this time. At this time you press the brake. So total distance combined will be the stopping distance of your car. So that is point 4 done. Remember, thinking distance, the time taken for you to realize you need to brake. And after you press the brake, the car has to stop itself. This is the braking distance. And stopping distance is the total distance of thinking plus braking and whatnot. And one short thing you need to remember is thinking distance does not really change unless you are, under the influence of alcohol or something else. Like your mind is, if let's just say you're in sane mind or solid mind, then the thinking distance does not change. And braking distance will change depending on if the road is dry or wet and whatnot. So braking distance can change depending on the car. And if your brakes are like faulty or something, that can also happen. But in the question, the brakes are not faulty. You will only come across if the roads are wet, dry, and stuff like that. So that is all on braking distance. Braking distance does change. Stopping distance is just the total distance, add them up if you wish. So explain number 5. Explain the factors that affect thinking. Acha. So I already mentioned all these points before number 5. Okay. Yeah, tiredness is also a thing. If you're very tired or something, then you might not pay attention to the road. Alcohol, drugs, low tire surface. So if your car is very heavy, then you know your car will push down the road a lot harder, and so the tires will be much more effective in stopping your road because they can they can generate a lot of friction. If you're very heavy, the tires will generate more friction and stop you faster. And the road conditions, I did mention wet and dry. Tire surface is a niche thing, like unless your tires are actually damaged or anything, right? The tires will be pretty good. But yeah, do keep in mind tire surface also matters. So now elastic deformation. Know that forces may produce a change in size and shape of an object. So it's also kind of common knowledge. If you, let's just say, squeeze a bottle, squeeze a, how should I say, plastic bottle. So let's just say this is a plastic bottle, and if you squeeze it very hard, right? If you, let's just say, push over here and push over here, if you squeeze it very hard, the plastic bottle will bend under pressure. So force can change the size and shape of an object. This is understandable. Define the spring constant as force per unit extension. Recall the equation this. So we have a equation for spring constant, which is force per unit extension. So what is extension? Extension being that, let's just say you have a string, you have tied the string, there is a hook here, and you are pulling this part with, I don't know, 10 newtons, right? So this is the force, 10 newtons, and extension. Extension will be, let's just say this spring or whatever, this thing has stretched a bit due to the force. So the stretch itself will be, let's just say, 2 centimeters. The spring itself, like the total spring from this part to this part was let's just say 10 centimeter, was before you hung up the weight, was 10 centimeter before. After weight, it becomes 12 centimeter. So 2 cm was added, extra extension. Let's just say from here to here was extension. And K is the spring constant, F is the force, X is the extension. So F equals Kx. This is the equation you normally will write, F equals Kx. And you can rearrange it to make, K equals F by X. F is the force and Kx is the extension into spring constant. Always remember, this is the extension, not the entire length of the spring, only the extension of the spring. Okay, sketch, plot, and interpret load extension graph for elastic solid and describe the associated experimental procedures. So, sketch, plot, and interpret load extension graph. Okay, and you might have realized that F equals to Kx, right? So this is basically F is proportional to X. So F increases, X will also increase. The more force you are giving, the more the extension with a constant. So this constant can be any number, the 20, let's just say, or let's just say 30 or 40 or anything, any number. So there is a constant number, some constant offset multiplied with the extension. So this is a pretty very basic formula. Okay, let's draw the sketch and plot and interpret load extension graph for a elastic solid and describe the associated experimental procedures. So how do we draw? Okay, so let's just draw two axes, and this will be our load, LOAD. Load will be 10, not 10. Load will be, as we move upwards towards the graph, load will increase, and this is newtons. The units will be newtons, so bracket newtons. And as we go along this way, this will be extension. Asha, we'll actually change it. We'll change it. We will put load here. Load will increase as you go this way, and this will be newtons, load in newtons, and this way you will have extension. So let's just write x in extension, and this will be cm. Okay, insane. So as you add more and more weight, what will happen? Load and extension has a proportional relationship. So as you add more weight, the extension will also increase accordingly. So it will be a straight line because proportional. The straight line means it is proportional. If it is curving in any direction, like if it curves upward, curves downward, this is not proportional. And the formula does, say that this is proportional. Say if we write f equals kx, it basically comes down to f is proportional to x. So the formula must be this. And for an elastic solid, right? Elastic solid means when you stretch the thing, right? When there is an extension, if you remove the load, the extension will also go back down. There will be no more extension. So if you remove this 10 Newton load, it will go back to 10 centimeter. This is what they mean by elastic, that it can stretch itself and then come back to its original size. And associated experimental procedure. Experimental procedure, I guess it basically means the mere act of like adding more weights, then removing the weights one by one and whatnot. And weights must be, let's just say, equally distance from each other. Like you can add 10 newtons, 10 newtons. If you add 10 newtons, you can plus 10 newtons and whatnot. You cannot just add 24 newtons more and whatnot and then just randomly plot a graph. You have to plot a sensible graph, is what they mean, I guess. Define and use the term limit of proportionality for load extension graph and identify the point of graph. Understand of basic limit of much. Elastic limit is not required. Okay. Understanding of elastic limit is not required. Okay. Same sign. So what is the limit of proportionality? Imagine this is a ceiling and this is a spring. So as you keep adding more weights, let's just say once you add 1,000 newtons, right? 1,000 newtons is basically 100 kilograms on this tiny spring and whatnot. So you might realize that one spring can hardly hold 100 kilograms, and the spring will then either break or deform, meaning it will not come back to its original shape of, let's just say, 7 centimeters here. Once you remove this load, all right, it was, let's just say, after adding 1,000 newtons, right? After adding 1,000 newtons, it came up to 14 centimeters, like, so there was 7 centimeter extension. Once you remove the load, there is no more 1,000 newtons. The spring does not come back to the 7 centimeters. It stays at this point, which is 10 centimeters. So 3 centimeter was extra added to the spring, so meaning it was deformed. It did not come back to its original shape. So this is the, let's just say, limit of proportionality. Once you reach this point, and if you add more load, right, the extension will go like this. So either the spring will completely tear off, meaning the extension will just go up to infinity, right? If the spring tears off and whatnot, the extension will be very high. Or the car will go this way. It will not extend anymore. Because there are a bunch of coils in the spring, right? If you extend it in more and more, the coils will just become a straight line and it will not extend anymore. So it will go up like this and it will plateau. And then if you keep adding, it will break again. Let's not go that far. So you just have to remember that the spring will either break, meaning extension will go high, or the spring will just, become flat. So it will become a straight line. And once you see a curve like this, right, if you see a graph with load and extension, there will be a straight line and there will be this plateau or this kind of plateau. This point will be the limit of proportionality. The limit of proportionality is basically a point after which the spring goes through deformation or breaks, does not return to its original point. Okay, so we see this one, we saw this one, and we sketch the graph. We define and use limit of proportionality. Define and use. What is the definition of limit of proportionality? So the limit of proportionality is a point after which the spring does not return to its original size because it is now deformed, right? A point after which the spring does not return to its original size. So this will be the definition. Circular motion. Describe quantitatively motion in a circular path due to a force perpendicular to the motion as speed increases if force increases with mass and radius constant. Radius decreases if force increases with mass and speed constant. An increased mass requires an increased force to keep the speed and radius constant. Okay. So first point is speed increases if force increases with radius and mass constant. Okay, so how do we see speed increases? And remember mass and radius constant. So let us erase. Okay, my bad. Let us erase this thing. We draw a circular path. Okay, and this is the center. And remember this circular path, there is a car or an object. This object is going forwards and there is a perpendicular force. Let's say there is a perpendicular force this way, perpendicular force this way, keeping the mass in this circular orbit and whatnot. So speed will increase. So let's just say S. Okay, let's just write V. S is distance. So V increases, but mass M and R do not change. So no delta, no change in the radius. So radius does not increase, mass does not increase or decrease. So how will we increase the velocity without increasing these two things? So first, let's understand what happens when you are in circular motion. Your speed is constant, assuming your speed is constant. Assuming your speed is constant, if you are, let's just say, as your speed is constant, right, meaning there is no resultant force, there is no acceleration. So let's just say your speed is this 20 ms. You're moving towards the left, and we need to keep you in a circular orbit, meaning you need to slowly move towards the bottom and whatnot. So if this car is going forward and forward, right, as the curve happens, right? If you're moving forward, let's just say you're moving this way, the curve, you have to follow the curve, so you have to move downwards a bit. So a perpendicular force is needed to move you downwards a bit. And why perpendicular? Because if you zoom in and in, if you zoom into the circle, right, you zoom into this track, if you keep zooming in, it becomes a straight line almost. There is only a very slight amount of bend, right? There is a very slight amount of bend. So if you just add a slight amount of perpendicular force, you can bend the head. Let's just say this is your head. If you add a perpendicular force, your head will now be in this direction, right? Here and here. So you just have to imagine it. I can obviously pull up a simulation or something like that, but imagining that is not really hard. So just remember, there will be a bend and you have to follow this bend, and there will be a perpendicular force needed. As this force is exactly perpendicular, right, your speed will not change because there is no force acting against you, right? Exactly perpendicular. So the xy plane, if you imagine the xy plane, if there is a force in the y plane which is upwards, and if there is a force in the x plane, the resultant will be, let's just say, this way. So over here, the resultant will also be somewhere here this way. But the resultant does not matter. We only care about the fact that if it is exactly perpendicular, this 20 meter per second speed, right, this will not increase. Why? Because if there was a slight amount of force this way, let's just say 10 newtons, then the 30 newtons would be the total, speed. Why? I'm saying newtons again, but think of this in terms of speed. Because if there was a force, there will be an increase in speed. So there is no resultant force here. So this is the end goal or end takeaway. There will be no resultant force towards the left or towards the right. So the actual speed of the cube will not change, and the actual speed will always be 20 ms. There, the only force that will be acting is a resultant force towards the center. Let's say this will be the center. There will be a force towards the center. So now we get it. The speed will not change. Why? Because the speed is in direction x and the force is in direction y. So they do not add up. And if you look at this example, the resultant speed, the resultant speed will still be 20 ms. The speed will not increase, it will just change direction. So this is what I'm getting at, right? The actual value of the speed will not change. The direction, as this, velocity, I'm saying speed and speed again, but this is velocity. Velocity will change, it will just change its direction. This is a vector, so it will change its direction. This might be a bit complicated, but circular motion is only going to get this complicated. It is not going to be harder than this. In later classes, circular motion will actually be pretty hard. So here, this is just the basics. So if you understand it once, it will be, not a problem anymore. So in short, the force that is towards the center is only required to keep the direction in check and change the direction over and over. If there was no force towards the center, the object will just keep moving, and just it will fly away. And this force, right? This force will always change direction. So if the car was here, the force will be this way. So it will always point towards the center. So the force will keep changing direction. Okay, we now get it. There is a force and it will change the direction of our speed of the car. Our original goal was to see speed increases if force increases with mass and radius constant. Why does that happen? Speed increases if force increases. What force? The force towards the center. So if you move faster and faster, let's just say Your speed was 200 ms, right? That would mean you are going like, let's just say 200 times or 10 times the distance, right? 10 times the distance. If you're moving 10 times the distance, that will mean the circle here, right? You will fly up the circle very fast. So you need to change your direction, right? You need, if you're going straight, you need to curve inwards. You need to change your direction very fast. Now we understand, right? You have to change your direction very fast. How do you change your direction? With this force. So if you're changing your, or if you're traveling very fast and you need to change your direction faster, then you need a higher force. So this inward force will be very, very high. So you can keep changing your direction towards the center. And if you're moving towards straight, you can go towards the center. Again, if you're going straight, keep moving towards the center. It will constantly pull you towards the center. Remember that. So if the force increases, right, the inward force increases, you can move faster throughout the circle. This force is only responsible for keeping you in a circular path. So this is why if F increases, V will also increase. V meaning the velocity you're traveling with. If you're going straight, the velocity will be straight. So this took a bit of time to explain. If you need to understand this one, just rewind a bit, look at it again. You will get it if you like look at it three times ish, I think. And if you do not understand it at once, then look at it today, try to understand it, keep it in your mind, and come back tomorrow. So take a bit of time. Okay, so next is radius increases if force increases with mass and speed constant. Radius increases if force increases. Okay. Radius decreases. Yeah, I'm reading it wrong. My bad. I'm like radius increases, force increases. This sounds a bit wrong. So yeah, radius will decrease. Radius will decrease if force increases with mass and speed constant. Let's just say m is now constant and speed is now constant. Speed again will just write b. So del b, no delta or no change. Mass and velocity have no change. Mass and velocity no change. Radius decrease. Radius decrease. F increase. Again, we think of a circle and radius will decrease if the force. So if the force increases, you will go inwards. If you are traveling straight, right, you will go inwards. You will go inwards. If the force increases, you will move inwards more and more. As you move inwards and inwards, your radius will decrease and you will stay over here in this trap. So once your radius increases enough, right, your bend will stabilize. You will not go inwards anymore. If your force increases, your radius will decrease. Just imagine it in your mind as you're going straight, you are bending towards the downwards and whatnot, and you're repeating this motion, right? You're going straight, and this perpendicular force is bending you inwards. And if this perpendicular force increases a bit, will bend even more. Will bend faster. If you bend faster over time, your radius will decrease. Next point is an increased mass requires an increased force to keep speed and radius constant. If your mass increases, you need more momentum. You need more momentum. What is momentum? Your car has 20 kg mass, and this is your speed. Momentum will be, or P is your momentum. Momentum will be m into v. M into v. mass into velocity. So 20 into 20. This will be your momentum. Momentum, let's just say, is in this direction. If you need to change your momentum, if your mass increases, right? If your mass is 40 kilograms, then your momentum will be even higher this way, right? So before we looked at what happens when speed increases, right? Velocity increases, force increases, right? So velocity increases meaning speed increases. Now, speed is the same, right? Speed is 20 meters per second, but your mass has increased. So as you can see, if mass increases, that basically also means speed increases. Look at it again, right? In the first scenario, your mass was 40, no, sorry, your speed or your velocity. Speed and velocity is the same. Let's say your speed was 40 ms and we find out our momentum. So P equals m into V. So 40 into 20. This was your momentum. And this momentum is going this way, right? Going this way. This is your momentum. This arrow represented is P. So if you're going this way pretty fast, you need to bend inwards pretty fast. We understand that one. And now example number 2. Here, the speed is the same, but your mass has increased to 40 kilograms. So now we multiply by 40. So your momentum is again the same as before, same as this one. Now you understand, right? If your mass increases, that basically means your speed is increasing. Not exactly, but in terms of momentum, the value is the same, right? Imagine that. So now that your value is the same, that means you have to bend inwards pretty far or you will just fly away. You will just fly away. So there is a higher force needed to keep you bending inwards. Sorry, my bad. So okay, so this one is a bad example. We'll erase this one. We'll imagine a door handle. So there is a pivot here, and this will be your door handle. So, and this is the keyhole. Imagine you need to rotate this door handle, right? You will need to rotate this door handle with 20 Newton force, right? And this door handle is 5 centimeter long, 5 cm. And if you apply 4 newtons on this door handle over here, over on this direction, if you apply 4 newtons here, then this will be enough to rotate the door. How? So force will be 4 newtons into perpendicular distance will be 5. So 4 into 5 equals to 20 newtons, let's just say. So perpendicular distance will be in meter. I'm using cm here for convenience, but perpendicular distance will always be in meter because you always use SI units in physics. So this is basically it. Force into perpendicular distance from the pivot. And this is more or less on force and whatnot. So moment is this force into perpendicular distance from the pivot. And this basically helps you in everyday life, right? If this door handle was 20, only this knob, right? This knob, you have to rotate this knob with 20 newtons. It will be a bit harder if you have slippery hands. But if you add this handle, this will make you rotate it faster. And now a more harder example. Imagine a seesaw over here. So there is a rock. You need to move this rock. And this is 2 meters. 2 meters. This will be 1 meter. And this rock is 100 newtons. If you want to move it up, right? If you want to move the rock up, you will need to provide 100 newtons to move it up. So just add the weight is 100 newtons. But if you add 50 newtons this way, 50 newtons, you can move the rock up. How? So force into perpendicular distance, always remember that. If you add perpendicular distance here, so 2 into 50 will be 100, 100 newtons. And as you can see, this is a single piece of wood or whatever, right? They are connected. And this rock, if it wants to move upwards, you have to provide more than 100 newtons or equivalent of 100 newtons through this rod to move it upwards. So we have to use equation 2 times. On this side of the rod, 1 times force into perpendicular distance. On this side of the rod, right, this side of the rod, we have to use the equation again. So our moment will be our moment will be equals to 100 newtons. So let's just say 100 will be a resultant equals to, we know our weight, right? Our weight is 100 newtons. So how much distance do we need? We need 1 meter of distance. So force into perpendicular distance into 1 meter. So this will give us a moment or moment of 100 meters. What I'm getting at is the double distance here and the double weight here, they cancel each other out. This is a harder example. So this might be, needing a bit more time to understand, but basically this is how seesaw works. A moment is generated this way, and then it has to be cancelled by the moment this way, and leading into the thing called principle of moments. So clockwise moment and anti-clockwise moment must be equal. Again, imagine this. This now is a pivot hanged on the wall or whatever. A water bottle is here. A water bottle is here. This is 20 newtons. Distance is 5 meters. So force into perpendicular distance, 5 to the 10, so 100 newtons, newton per meter, newton meter, sorry, newton per meter, not, this will be 100, oh my god, bro. So this will be 20 newtons and this will be, okay, 100 newton meter moment, newtons into meter, not newton per meter. So this is the moment. And as you can see, if the moment is generated this way, the bar or whatever, this will rotate this way, this will rotate downwards and whatnot, and it will rotate, keep rotating. We need an anti-clockwise moment. So this is clockwise moment, right? Because the clock moves this way. And what is the anti-clockwise moment? This way. Anything that moves this way. Anything that moves from this way to this way. So from right towards the left. If you go towards the left this way, this will be anti-clockwise moment. Okay. We need anti-clockwise moment, and we need 100 Newton meters to cancel this right-sided moment. So over here we have only 2 meters of distance, right? The rest is unusable for some reason. We will have to employ 2 water bottles or we'll have to employ a bigger water bottle, like a very fat water bottle. So we'll have to employ a very fat water bottle. This water bottle will be 50 newtons of weight. And if we multiply 2 meters into 50, we'll again get 100 Newton into meters. This will be our clockwise and anti-clockwise. They will cancel each other out. So this is here the same thing, but they do not cancel each other out, right? This anti-clockwise moment is greater. So it is overpowering this clockwise moment and moving this rock upwards. Again here, if we add a bit more weight here, then this will rotate anti-clockwise and the water bottle will rise up and it will slide towards the left. It does not matter. Basically, when this happens, right? When the forces are unbalanced on one side or the other side, we call this not in equilibrium. So the moment is not in equilibrium, they are not balanced. But if it is in equilibrium, right? Clockwise and anti-clockwise moment are equal, then we call this equilibrium. So objects in equilibrium. So describe an experiment, and if they ask you to describe an experiment, literally just say this experiment I showed. So you literally just write, we set up a pivot, and then we put weights on one side and we put weights on other side, and we watch if they are balanced and whatnot, or if they move to one side. Basically, you'll think of this pivot thing. You will write up how much distance you keep each weight from the pivot and whatnot. Just write it up like 3 or 4 marks. If we get a question like this in question paper, I'll surely try to solve it. So turning effect of force is done. Center of gravity. Describe quantitatively the effect of position of center of gravity and stability of simple object. What is center of gravity? A point on an object where all the weight of the object seems to act upon. This is the literal definition. If you want to write it down or anything, a point on an object where all the weight of the object seems to act upon. If we have a water bottle here, this will be, let's just say, the center of gravity. So if we add a toothpick here, literally a toothpick, then it will be stable. Why? Because on this center of line gravity, right? Center of the line on center of gravity, right? On this line, all the weight of the object will seem to act upon. So if you support this one simple point on the object, right? If you support it with a toothpick, the object will be stabilized, it will not fall. If you place a toothpick here, it will just fall towards the left. If you place a toothpick here, it will fall towards the right. So where all the weight seems to act upon, it does not actually act upon here, but as it is a solid object, it seems to act upon only one point, one singular point on an object. This is the center of gravity. Describe how to determine a center of gravity on lamina and whatnot. How do we, so if imagine we have this irregular 2D object, right? This is a sheet of cardboard. How do we determine the center of gravity? We have no idea. So we have to set up an experiment. So imagine a stand here, a rod here, use a toothpick or a pin and take one edge, right? We take this edge, this edge, this edge, just some kind of an edge, and stick it up on here, right? Let's stick it up on here, then let it freely rotate. Take this, stick it on here, let it freely rotate. So once it freely stops, if you hang it up over here, just give it a push towards the right and push towards the left, so there is no friction keeping it stuck. Once it is freely moving, right, move it like a pendulum for a bit and then let it go. After it stops moving, then it is in equilibrium, let's assume. And then take a string line and tie it around this knot, right? If we look from a sidewise view, right, this will be your stand, this will be your thing, there is your pin, this will be your cardboard, right? This will be your cardboard, and add a string here, and the string will be hanging. Let the string hang in a straight line. Okay, then mark a line here, right? Mark a line straight as the string shows you. Then take another edge, then hang it on the toothpick or pin, and then use the string again. So now you will, let's just say, get a line like this. So once you get two lines, the intersection of these two lines will be your center of gravity. That's basically it. So this is how you find the center of gravity with the plumb line, or yeah, plumb line, plane lamina, center of gravity. And last point of this topic, describe quantitatively the effect of the position of center of gravity on the stability of simple object. So what role does center of gravity play to stabilize objects? If your center of let's just say this is the ground and you have one object here, this object goes like this, has a very bad base and whatnot, so the center of gravity will be very high. If a very tiny force acts upon it, it will instantly fall downwards if the center of gravity is very high. And if you think about a pyramid has a very low center of gravity. If you are a very large force, very large force, only then it will topple over. This is basically it, right? This is literally common sense. You have to look at the center of gravity. They'll point out, right? The question will point out this is the center of gravity, and they will ask you, is this a very stable object, mediumly stable object, or not stable object? You'll just look at the object and give your answer. If the center of gravity is closer to the ground, means it is very stable, it will take a lot of force to push it over. If the center of gravity is very high from the ground, that means it is unstable or unstable object. This is done, and this is basically it. Let's move on to the notes if we see anything useful. So I'm gonna scroll through and silently read, and if I see anything interesting, I'll point it out, but I'll scroll through a bit and you can see if you like anything. So after that we have momentum, but we'll yeah, we'll see that in the next chapter. We'll probably cover 1.6 and 1.7 together, but that is all on 1.5. And yeah, I am scrolling through the notes. If you want to read it, you can pause and read. But yeah, that is all for today, so goodbye.